let me introduce Pierre Lochac, who's probably the only person who's giving a seminar for both the mathematical group and the planetary group. And at least in the field of dynamical systems, he's done some nice work on the exponents for the Nechorshev theorem. And he's going to talk about stability of Hamiltonian systems in that context.
Okay, well, thanks for inviting me to switch program for a day. So I'll try and give some sort of, let's say, gentle survey of Hamiltonian perturbation theory. I should say with an eye towards celestial mechanics, the trouble being that I know very little about celestial mechanics, so you will tell me, you will be the judges whether it's relevant or not, quite simply. So you start from your Hamiltonian. I'll just comment on that. Okay. So what does it mean? Maybe you already do not necessarily like this. So this is a Hamiltonian. You have P and Q are the action angle variable. You have an integrated part, I should say, which depends only on the action variables. And then you have a perturbation. So maybe in some of your cases it's already optimistic, or it's not optimistic, but it can be very difficult just to write the Hamiltonian that way. I mean, if you think of a planetary problem, H of P would be the sum of the two-body problems without interaction, and then you you switch on, so to speak, the interaction between the planets. But just writing the three-body problem this way is quite cumbersome. But so the first thing, which may or may not be realistic, is I assume that we start from something like this. Actually, not quite, because, okay, so this is, this in a famous quote, in a famous sentence, Poincaré said it was the general problem of dynamics and celestial methods, which is not quite true, but okay, it's reassuring. There are other cases where you can apply what I'm about to say, which is you take a Hamiltonian, whatever it is, and then you have to find some invariant objects, like equilibrium points or periodic trajectory, where if you're a mathematician, you will say tori, because a torus of dimension 0 is a point, a torus of dimension 1 is a periodic trajectory, and a torus is a torus. Sometimes you find other objects, like typically how do you call them? Invariant manifolds attached to, for instance, hyperbolic objects. Okay, so if you start from some invariant objects in any Hamiltonian, near these invariant objects, you can have a perturbation theory where epsilon will essentially be the distance from your invariant object. So either you start from, which I will do, from this Hamiltonian, or if you're lucky, you just, by pure serendipity or whatever, find an invariant object, and then sometimes you can write your Hamiltonian in the vicinity of your invariant object as a perturbation of something, where epsilon would be basically the distance from your object. Okay. Then what can you say about this? So the P's will be, as you know, typically the semi-axis and the eccentricity of your planets, for instance. What do you do? So one thing I'd like to, for instance, to say that there's a core reservoir of methods which are always the same, and which tells you that typically averaging, normal forms, adiabatic invariance are one and the same thing if you view it properly. I mean, maybe physically it's not exactly one and the same thing, but the methods are exactly the same. It's completely homogeneous. So before Poincaré, very famous people would follow trajectories by trajectory, or trajectory by trajectory, and typically they would write down formal expansion for one trajectory. So Poincaré had the very modern idea of genius to start normal forms, which means instead of, so now this is in your space, so let's call it, let's say D, a certain domain is Rn cross Tn. Oh, by the way, Tn is just the circle, okay? So these are phase variables, so it's just the circle. So T is R naught Z, like mathematicians like to write, which is just the circle. And so it's in the phase space here. What was I about to say? Oh yeah, and what Poincaré, the idea of Poincaré was, what if we change the space, and then so that we'll conjugate the system, and we'll see if it looks better in the new coordinates. So in down-to-earth term, it means changing coordinates rather than following trajectories. It was an idea of genius. It's actually a thesis on normal forms. I don't remember the title, but normal forms on differential equations. So that's what we do today. I mean, usually that's what we're still doing. So you change the coordinates. How do you change the coordinates? We're in a symplectic or a Hamiltonian, which is even better, so to speak, than symplectic. So you want to have change of coordinates, which are according to the group you have, which is symplectic here. So they have to be symplectic. So now you have two ways to do that. Either you use canonical, we want canonical transformations. So these are called canonical transformations. So either you use generating functions, or you use Lie series. So I should say change coordinates. Change coordinates, so to speak, in order to improve, quote, your system. So improving means, in the best of all worlds, would be making epsilon smaller. If you make epsilon equals 0, so we know that for epsilon equals 0, well, maybe I should have said that for epsilon equals 0, you have p dot equals, in this system, you have p dot equals minus epsilon df dq, and q dot equals, well, yeah, the same, well. And then, of course, if epsilon equals 0, p dot equals 0, tori are conserved, and then you have this Liouville-Arnold, Liouville actually, picture. Now you also write omega p to be the gradient, yeah, I'll write q dot. Well, omega p will be the gradient of h, okay? So it's a vector, an n vector. So this is the frequency vector. So of course it's very important since q dot is nothing but omega p plus epsilon df dp. Okay? So that's your basic thing, your basic setup, and omega is the frequency vector. Okay, so now you want to improve your system, which means make epsilon smaller. So these, what are the Lie series? So the two things are, so to speak, reasonable, except Lie series, which is a little more modern, is really sort of more efficient in terms of even implementing it on a computer. I mean, implementing it on a literally, formally. In literal how do you call it? Yeah, formal calculus, not numerically. So how do you, what are Lie series? That's very easy. How do you manufacture a symplectic transformation? You take a Hamiltonian, and you know that the time t, and I know that you know that if you have a fixed time, let's the time one of the flow of a Hamiltonian is a symplectic transformation. Okay, so what you do is you take an auxiliary Hamiltonian, which I write this, which plays the role of, here would be the generating function. It's actually very closely related, and you integrate this Hamiltonian for a certain time. The certain time is what? The certain time is epsilon, because you want to produce a change of coordinate which is at size epsilon. Okay, no more. So if I integrate the Hamiltonian, which is this, in terms and I take the epsilon time of the flow, then I have a symplectic transformation which is epsilon close to identity. So how do you do it? Then you introduce the operator L chi, which is just bracketing with chi. Now, depending, of course, I'll do it wrong. I mean, it's a pure. It's a matter of convention, the signs, of course. So, I mean, it's almost a matter of convention, but you want to have the right sign. So, I just guessed, so it's probably wrong. And what do? You write e to the epsilon L chi. Well, and you say e to the epsilon, then I'll come back to this. There's not just a way of writing. E to the epsilon L chi will be of some function, g, which then g will be equal to h, but now it's g. Will be g plus epsilon L chi g plus epsilon square L chi square g plus dot dot dot. I mean plus epsilon n over n factorial L chi n g plus whatever. So there will be, let's say, g plus epsilon chi g plus epsilon square over 2 chi g plus whatever. Why do you write? Why isn't this reasonable? Maybe you should. It's good to have the geometric picture in mind. L chi is nothing but, how would you call it? A vector field. Okay, you have a vector field and you're transporting along your vector field. For mathematicians, maybe I should say that. What is Taylor's formula? Compare with Taylor formula. What is Taylor formula? You have a function, and you have a function you compute at the point x, and then you want to compute at the point x plus a, say, or x plus y. So, or a. Then you have an operator, which is d over dx. I mean, which is well, here I have only one variable, so d dx. And if you have a function of one variable, if I do this, d dx of g of x is g of x plus a. And this is g of x plus a g prime of x. I mean, this is d dx plus a squared. Okay, plus blah, blah, blah. This is the exact same formula. The Taylor's formula is this. And we're doing this. So we're saying this is the time a of the translation, and this is the time epsilon of the Hamiltonian chi. So we're doing the exact same thing, but we do it in a symplectic context. Okay, so now we apply this to h. So we do e to the epsilon L chi of h, and we get, so that it's h plus epsilon f plus, plus epsilon f plus epsilon chi h plus things which I dare not, I mean, plus epsilon square something. It's very, very optimistic to imagine that they are on the order of epsilon square. Now maybe I write the next terms. It should be epsilon square, what is it? I'm lost. Oh, chi f plus epsilon square over 2 chi h. Yeah, should be okay. Okay? Oh, and I should say something. Yeah, don't forget, Taylor's formula is like that too. Here, I don't have to say plus blah, 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 blah. I can say plus g double prime of y, where y is somewhere between x and x plus a. I don't know why, of course. Okay, that's the, well, it's one of the form of the remainder. Here it's exactly the same. I'm following the flow. So actually I can put, of course all the variables are missing. So you have PQ, blah, blah, blah. And here it's at a certain point, P star, Q star, which is along the trajectory, along the chi generated trajectory from PQ to whatever. Okay? So actually, no, this is very important that you don't have to do the blah, blah, blah. If you want to make, if you want to how do you call it? To make real estimates, at some point you will use this. Now, this is, I think, the most important computation of all. So here you have h of p plus epsilon f plus. So I would like this to be. It will lead, well, I don't care. Do you have a plus or minus? I really don't care. So chi h is d chi. Oh, so dh over dq is 0. H depends on p only. So it's d chi over dp. Well, if I refer to this convention, it's this. Yeah. This is a scalar product. This is a dot product. Huh? This is the dot product between two n vectors. Plus, plus here I get nothing, okay, from the second term, plus same thing. Oh, I write it, okay. Okay. Now, now what would I like to do? I would like to, so chi was still free. I choose chi. Chi is just the thing which will affect the change of coordinates. So I still have it at my disposal, so to speak. So by choosing chi appropriately, I'd like this term to vanish. If this term vanishes, we agree that, well, it will be of order epsilon squared. And it will be truly of order epsilon squared because, as I told you, well, it will be truly like that. Let's say, well, okay, we'll come to assumptions later. I mean, soon. So this thing, omega p plus dot equals minus f here. This is the equation which has to be solved, and we'll generate small divisors. This will be the small divisor equation. It goes under the name homological equation because, well, but that's the main equation. No, well, okay, in this, if you put it this way, it's the main equation. So how do you do it? Well, normally what you do is chi of pq, and you just expand in Fourier series like this. Okay, maybe you're on 2 pi, it doesn't matter. It's easier. I mean, you say your circle is length 1 instead of 2 pi. You don't care about, of course, you don't care about the constant. Constants, I mean, you can always add a constant term, it doesn't matter. So d chi over, so this will be, so the solution in, oh, and then you do the same for f. Fk, Fp, e to the I kq. So quite often you will maybe want to have polynomials here. I mean here, sometimes your perturbation will be a trigonometric polynomial. So this, which means this sum will be finite. Okay, it may or may not be finite. But maybe I'll come to that. Now, I'm facing the hard task of solving this equation. Well, let's do it. So you have the sum. So I do this. of omega p dot k I, well, there's an I somewhere, e to the I k q equal this minus f of pq. So I get, oh sorry, and here I have a k s. So that gives me that this is equal to I fk of p over omega p dot k. Okay, so you get this. So are you happy? Well, yes and no, because these are the famous small divisors. I mean divisors, but they might be small. So now immediately you have two cases. Immediately you have two cases. The quote linear, or maybe you'd like to say isochronous case, which is omega p equals omega independent of k, of p. That's p independent. So of course this is, or maybe you want to call it harmonic. Okay, so it's all the same. So omega, the frequency does not depend on your action variable. So it's the linear, not necessarily approximation, but it's, so if you have even an infinite lattice or whatever, and it happens to be linear, then you're in this case. And then your problems, your denominators, omega p dot k, which is omega dot k. So k is a vector in Zn. You should have told me that this was Zn, not Z. Okay, so this is multi-variable. So in Zn, so it's omega 1k1 plus omega blah 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 plus omega nkn. Well, this depends entirely on the arithmetic of omega. Okay, so if omega in Rn is, say, Diophantine, I'll explain what that means. Then, well, that I will not explain in detail. You get what I call Gevrey estimates, which are exponential. Stability estimates. Oh, plus one condition which you won't be necessarily much interested in, and if and h is, well, in that case, let's say f, because h is just omega dot p plus epsilon f. It's the linear case, okay? So that happens to a variety of situations. Again, it can be near, it can be Hamiltonian like this. Okay, so it can be a linear lattice, it can be anything. It can be near a linear, an elliptic fixed point. It can be near a Km torus. It can be near an elliptic object, an elliptic invariant object. And then you might end up with this kind of things. And then you have stability exponential. Oh, okay, so I'll explain this. What it means. So yeah, the other condition is F analytic. Wait, no, it's not purely, it's analytic, I didn't say academic. No, it's not completely academic, I'll explain why. Although, well, maybe to some extent it is. I mean, it's wrong if it's not the case. So what do you do? So first, what is Diophantine? Diophantine means something which is like this. You want this thing to be not too small. No, yeah, not too small, since the inverse is not too big. So Diophantine means there exists two numbers, tau gamma, well, tau being more important, of course, than gamma, tau is the exponent, such that this for all k non-zero, non-zero. Here maybe you should have told me that this was non-zero, because again the constant doesn't matter. But if it's zero, it's not that is not good. and k is basically, well, yeah, no, let's say k equals this. Okay? So you have, it's just the sum of the components, the length of okay. So, and in fact, one proves that tau has to be bigger than n minus 1. I mean, this is not a condition, this is in nature. In fact, and this is quite important because it tells you, the n minus 1, it tells you that this deteriorates when n goes, n becomes larger, which is very, I was about to say moral, because of course the denominators get worse and worse. I mean, not of course, but as the dimension gets larger. And the way it gets larger, completely independently on your system and whatever, it's purely arithmetic in this setting, which is the linear setting, which I like to call the Gevrey setting. I'm not explaining why. Gevrey was a French mathematician who investigated other things, but somewhat related, somehow related. Anyway, tau is bigger than this. There's nothing to do against that. That's nature. I mean, that's numbers, purely geometric number theory. And so you see that it deteriorates. And now you have to, you look at this equation. We have chi k equals fk over omega dot k. And so you see that omega dot k is on this, like this. But now the fk's are the harmonic of your perturbation. So you don't want these harmonic to go too fast, to grow too fast. Even if at stage 1, so we're still at stage 1. At stage 1 you had a polynomial, but you're going to iterate this. And already at stage 2 it won't be a polynomial. It will stay analytic. But there is something about analytic function. If I have an analytic function in a strip, which is analytic in a strip, I mean in a complex strip of width, say, rho, then you know that the harmonic of that function, the Fourier coefficient of that function, will drop like rho, like this, times a constant, which is actually nothing but the norm of the function. So the size of this harmonic, of this Fourier coefficient, goes like this. And the small divisors are no worse than this. So you see that it converges. Okay? So, but okay, so that's because we assume omega dot 15. Otherwise, nothing would, I mean, it would not, it could be anything. Okay, for any omega, so if you don't say anything about omega, so if you take an elliptic fixed point, we're still in the stage 1 of the linear theory. So if you take an elliptic fixed point and the frequency is just anything, you'll be able to do something by doing something nonlinear, but you won't be able to do something this way, because this way it can be anything. You'll have 0 divisors, you'll have anything you like. Well, I'm putting things a little on the dark side because there are tons of, there are tricks and there are things and so on. So I'm telling the general thing. Okay, then maybe you can nuts and bolts and fight your way through God knows what, depending on the specific problem. But if you look at it from a general viewpoint, that's what you get. And okay, so and then okay. So what are Gevrey stability estimates? It simply means that, well, it simply means. Now, I iterate, okay? So you do it again and again and again, which means you have e to the epsilon L chi 1 now, and then you do e to the epsilon square L chi 2, and then you do e to epsilon cube L chi 3, etc. Okay? Now the etc. is, you will do it a number of times which actually depends on epsilon, if you want to do it. If I do it a finite number of times, I'll get a polynomial estimate, okay? I'll get, my Hamiltonian will be transformed. So why do I get an estimate at all? Because if at stage n I have hn plus equals omega dot p plus epsilon to the n f of pq plus remainder, this is a bit, then basically I will say that, what do I say? I say that p of t minus p of 0 is smaller than something small, I don't know, small, okay? For t smaller than, say, 1 over epsilon n. Okay, or maybe n minus 1. This is not too clean, okay? Just by looking at this, p dot equals, here p dot equals, p dot is on the order of epsilon n. Beware of the fact that these p and q's are absolutely not the same p's and q's that were written there. I should write them pn. They're different coordinates. Since each time, but the Lie series are very good because you can close your eyes very tight and you forget about all this. you just do it. Because, of course, each time you should rename the coordinates. But if you forget to do it, it doesn't matter. You just forget to do it. What you should not forget to do is to see the difference between p minus pn and q minus qn. But it's not big, because we've done this. And this is on the order of epsilon. And this is where you have an epsilon. Okay, we've done a certain transformation, but we have to be very careful. Huh? You have to estimate things and so on, but it's not too difficult. And if you're careful, you get something like this, which tells you that if you rig up things properly, so you will have something like p of t minus p of 0 smaller than, say, epsilon for, now I don't know, I don't remember by heart, but it will be something like e to the c to the epsilon to the tau, to the 1 over tau. Or maybe here something like that. Roughly, and I may be wrong by a. So the point is, this is our first exponential estimate. Maybe I should move on more quickly. So this tau depends only, again, on the arithmetic of your frequency vector. Okay? It cannot be too big because of this, which means this time scale will depend on the dimension. Actually, it will depend on tau. But if you're very optimistic, and I mean not very optimistic, if you take tau equals n minus 1, these are called very badly approximable vectors, but they're very good in this case. Then you will find this. So this tau will be roughly n, which is the number of dimensions, the number of frequencies, the number of degrees of freedom. Okay, so that's the linear theory, and again, it applies to the linear Hamiltonian, perturbation of the linear Hamiltonian, and it also applies, there was like, for instance, a phrase, sticky tori, maybe you heard the phrase, then that's is. That's exactly what you do. If you have a Km torus, I know you like to make fun of Km because the threshold are so small, the threshold of applicability are so small, but that's another, let's not talk about this now. But in any case, suppose again you spot an invariant object just by any mean whatsoever, then usually you can apply this. And the tori are sticky because epsilon will be some distance or something, or maybe for Km it will be the same epsilon. and you have trouble leaving them, exponential trouble leaving them. Okay, so tori, Km tori not by definition, but they live precisely for omegas which are Diophantine. Okay, so they live in regions of phase space. They have Diophantine frequencies. Okay, but this, I really want to insist that this is all a linear theory. Maybe I should say I should quote one phrase, which is Birkhoff normal forms. Birkhoff. Two F's? Yeah. Normal forms. So these were invented by Birkhoff near an elliptic fixed point. Well, it's already quite complicated in dimension 2, say. And okay. Now we go back to here and we tackle the nonlinear problem. So what is the nonlinear problem? Nonlinear. So nonlinear problem is and not isochronous or etc. It's omega p not constant. Okay, omega p not constant. So the best thing you can hope for is that, in fact, that's called d omega. Well, this is a quadratic form, and the best thing you can hope for is that this is non-zero. So, sorry. The determinant of this is non-zero. Okay. It's right, but let me try to be a little more. Well, for instance, if you have your favorite, of course, the two Hamiltonians what you want to compare are this one and this one. Okay, so here you have harmonic oscillator. Here you have, it's really harmonic oscillators versus rotators. Because here omega will be nothing but p itself, so omega equals p, and this will be 1. So it is so this is determinant, right? This is the determinant. Okay. So there is a big rub in celestial mechanics. It's basically never the case, apparently. So what happened is celestial mechanics is it's complicated from the point of view of mathematicians, partly because in between these two cases, okay, what did this case tell you? It tells you that p to omega of p, I'll say an ugly word, is a local diffeomorphism, which means if I give you the action, I give you the frequency locally, the frequency really varies with the action, completely, as much as possible. Okay, so this is locally one-to-one if you want. A local bijection, whatever. Okay, that's exactly what this says. But usually in celestial mechanics, it's neither one case nor the other. And that's one of the big source of troubles. For instance, this is a good condition for Km. Actually, this is a Kolmogorov original condition. So in celestial mechanics, let's say analyticity is usually not a problem, except for collisions. Of course, when things collide, they are not very analytic, and that's a problem. But that's very theoretical again. On the other hand, this is a big problem. For other branches of physics, this is not a big problem because, for instance, usually if you have a kinetic energy like this, quadratic kinetic energy, I will assume even better that not only this is not zero, but I'll assume something better, that this is let's say positive, that doesn't matter, positive, definite quadratic form. Well, it's positive definite, which means typically like this. Because then I don't mean to say it's like this. I mean it's actually anything. It can be much more complicated, but this is a quadratic form, and it's positive. It means you don't have. If not, you won't have stability, because near a hyperbolic fixed point you will not have stability. So at some point something like this has to occur if you want to be somewhat stable. But you can deal with things which are much weaker and so on. Okay. So you assume analyticity, which means you assume that your harmonic die quickly enough. You assume that something like this. Now you have two things. One is Km, which basically here we say Kolmogorov actually. The other one is exponential stability. Okay, which means stability over exponentially long times. We have stability over exponentially long times here in the linear case because of an arithmetic property. Okay. I'll say just, okay, what I can say about Km, which I think is useful, is the good news is if you make the small effort of going through these things, Km is not difficult, easy. Kolmogorov theorem stems from, there's a very interesting idea, which is the form of, so to speak, the shape of the normal form. But it's not difficult. I mean, I'm serious. It's not difficult because the core material is exactly this. Nothing more. I mean, a little more, but not much. And, well, as far as arithmetic is concerned, it's there. So I've already not proved that, I mean, I've given you half of the material you need in order to understand Kolmogorov's original theorem, which is the core theorem of Km theory. The rest are basically variants thereof. And there is a paper which, oh yeah, maybe there is a paper which you can go to the web page of, I think it's on the web page of Giorgilli. Giorgilli's web page. You go to Giorgilli's web page. He has many old papers. There are very few which have PDFs files because they're very old. And there is one which has a PDF file, and there's this one, a paper he wrote with Benedettin, Galgani, and Strelzin. Well, I'm not sure they wrote the four of them, I don't remember. Okay, which is Km for, I was about to say for physicists, but it's Km. I mean, it's not Km, it's Kolmogorov theorem. Very easy to read. I would really advise it, because then you will also learn on the way basically these things. And it's 20 page, 20 not very difficult pages. Okay.
And the paper of Kolmogorov was about how many pages?
4.
Yeah.
No. I know all the stories about these things, all the stories and all the jokes.
But the essential is there.
No, but it's no more. It's more than the essential. For somebody like Kolmogorov, it's very easy. Why is it very easy? No, it's very easy. Why? Because Kolmogorov started his career with one note to the Académie des Sciences, French Académie des Sciences, with a note about Fourier series that converge nowhere. Because at that time, which is 1920, there was a big issue of regularity of Fourier series and so on. So it was a big thing. So for Kolmogorov, the harmonic analysis involved in Km is babyish. I mean, it's not even, you don't mention it. Okay? And it is babyish, don't even mention it. The arithmetic is babyish, completely babyish. 5 pages of any. So if I were to be really mean, I would say this is not very easy. This is babyish as a theorem. The whole thing is the whole thing is the genius of no, but this is not to downplay the genius of Kolmogorov, because the only thing which is interesting in KM is the fact that he found a normal form which focuses exactly on the torus and proves its existence, and that neither Poincaré nor Weierstrass had seen. But that's the only thing that's interesting. The rest is totally, I mean, mathematically is non-existent. I mean, it's not non-existent. Okay, I'm going to exaggerate, but it's really easy. I mean, there are tons of theorems which are, I can tell you, I mean, 100 times more difficult. The only problem is that the only stroke of genius of Kolmogorov, and it's a big stroke of genius, of course. Where's the genius? In the normal form, in finding the torus, in rigging up the problem to say, that's what you have to find. And basically, I mean, Kolmogorov could have explained his theorem to Poincaré in 10 minutes. Okay, you can time it. 10 minutes, Poincaré would have understood. It's really not a problem. But it doesn't mean that there is no genius in that thing. I mean, the genius is simple. The genius is to find the simple thing which people hadn't seen, people being Poincaré and Weierstrass. Okay. Maybe I should erase this, and this is being taped, so very bad. But, okay, now there's a funny, okay, maybe I'll take Nikolashev's theorem. So this is 1954. So then came, Nikolshev, who was a student of Arnold, who unfortunately died young as many Russian people. He died 2 years ago, and he was quite young. I mean, he was less than 60, under 60. So that's a student of Arnold, and he proved the following theorem, that if what? We're there. So H is still H plus. If H is analytic, so H has to be analytic. So I should stress the exponentials come from analyticity. They come from this exponential. Okay? They come from the exponential decay of the Fourier coefficients of an analytic series. So if they're not exponential, if the decay is not exponential, the function is not analytic, it's just not exponential. There are many other things you can do, but this exponential comes from there. So H is analytic, and I'll be simple. It proves something more complicated than that. I mean, it has a condition which is called steepness, which is quite complicated to define, but it's a long and interesting story, but it's a story that has been continued now. But okay, take this. Then there exists A and B. So these are positive numbers. I'll explain what they are, such that for any initial conditions, so really I insist for any initial conditions, P of 0, Q of 0, then P of t minus P of 0, so the drift in action variables is not big. I put B because A is more important, and that's how I put it, but it's right. For t smaller than something which is c to the epsilon to the A. Okay, so over an exponentially long time, the drift in the actions is small. And I should say, such that for n, mathematicians hardly mention it, but maybe it should apply. That is, epsilon should be small enough. Otherwise, you're not going far. Okay, so that's considerably more difficult than the linear situation. And actually, the first proof his proof is really long and maybe I wouldn't say difficult. I mean, I would say in math people would make the distinction between long and complicated and difficult. It's not exactly difficult, but it's certainly long and complicated and cumbersome and very involved and etc. So it's very heavy. And you get this, and one thing you don't get at all, first you don't get the value of A. Actually, it came up with a value which was like 1, its value was like 1 over n squared. Went like, well, not even 1, a constant over n squared. So something which, okay. And you have no idea why it comes out. I mean, it doesn't mean anything here. It's just because you have long and complicated estimates, and you do the best you can, and something comes out. And what came out with this? That was okay. So I said there was a funny historical twist. The historical twist is that in 1954, okay, Kolmogorov proved this theorem, and by the way, Arnold, the A is precisely for the application to celestial mechanics. But there is a gap in Arnold's paper, which has been filled in by somebody called Jacques Fejos and Michel Hermann. So the application to celestial mechanics is Arnold, precisely. And the problem to apply to celestial mechanics is, of course, this, because this is not true. You have to weaken that and so on. And so there are problems which probably you don't want to hear about. And if ever you come to Paris, you can ask Jacques Fejos, he knows everything about it. Okay, but before Nekhoroshev, there was absolutely nothing of the kind over a polynomial time. Because here we go to an exponentially long time, but what about something much more modest, which is about over a time on the order of 1 over epsilon squared? There was nothing like that. So Nekhoroshev, he has a note in 71, and he wrote his paper, and the long paper in 77. So it's a little after that. I mean, it's 20 years after Kolmogorov, basically. And the funny thing is that in some sense you would have an intermediate thing, or something which is more elementary than Kolmogorov, which is prove this over a polynomial time, over 1 over epsilon to the n. Well, that did not exist, and nowadays it doesn't. Well, yeah, nowadays of course you can do it, but since you can do it over an exponentially long time, it's not very useful. Of course, you want to know about this. I mean, you'd like to know about this epsilon 0. In Nekhoroshev proof, the situation with this is very bad, because the proof is very involved, and there are many ingredients and so on. So of course that deteriorates the threshold of applicability. Okay, now what is it I wanted to say? Well, you can say yeah. Oh, now there was at least one person in the world, maybe he was alone, to worry about this. Was Chirikov. I mean, maybe you probably have all heard of him. Why? Because he had numerical experiments which were really bad, because the computers in Novosibirsk were bad, and we're talking about the 1970s, showing that Arnold diffusion should not be on this time scale with 1 over n squared, then the time square on the time scale like this was A equals 1 over 2n. Actually, no, I'm exaggerating. It didn't, I mean, I'm not saying the thing correctly. It didn't have numerical experiment. It even had arguments telling that this should be the correct time scale. So here, of course, you have Arnold. Arnold diffusion is really, of course, a very bad name, but let me write Arnold diffusion all the same. So this is 1964. So again, this is weird, because this appeared 71, much after these two things. The Arnold diffusion paper is difficult to read. It's again 4 pages, and it's probably much more difficult to read than this one. But you can try. I mean, it's a very specific system. So, but what is Arnold diffusion about? Arnold diffusion is about the mixing of ellipticity and hyperbolicity. And that's really difficult, because everything we do here is elliptic, meaning small divisors, rotation, Fourier series, and so on. Arnold diffusion about mixing hyperbolicity and ellipticity because you have invariant manifolds, hyperbolic objects, and so on. And that makes it very difficult, geometrically speaking. And Arnold diffusion is not so. I mean, this is complicated, but Chirikov had this thing that the time scale for Arnold diffusion should be this. It was it was not numerical. It's a formal argument, which is very beautiful in the style of Chirikov. Again, I advertise for Chirikov report, Physics Report 1979. Chirikov's Physics Report 1979. This is where he summarizes what he knows about the standard map and so on. But in this report, the last section is about Arnold diffusion. I think I'm basically the only reader of that paragraph, which I mean, I was inspired by reading that paragraph, and I knew Chirikov and so on. But the number of readers of the last paragraph of this, which is very difficult to decipher, should be very close to zero. But okay.
Almost impossible to read.
Yeah, but not for the same reasons, huh? Because not for the same reasons. For instance, it goes directly to tell you that, well, it should be like a Brownian motion, but near the boundary it should be a Levy flight, so you should get the exponent for the Levy flight, which should be like this, because it's really beautiful. But I understood his argument, and this argument is in the paper, in the long paper here. I mean, I formalized in this paper, in particular, I formalized this argument for this. Now, maybe, so now I'll finally mention, I mean, we're coming to a very familiar thing for me, I mean, old memories almost. So, very old memories. So, what I did was, well, it's okay, now you have exponential stability, I dare say much improved. I mean, much improved over Nierhorschev. So there are three things. Well, no, there are quite a number of things. First, as you mentioned in the title, you have this. Okay. So, but that's only one aspect. That's really only one aspect. It's reassuring and it's very good. So why is it good news? Because we also proved in a completely different paper. Okay, we're on the stability side. Now you have the instability side. We manufactured a Hamiltonian. It's completely bizarre and completely artificial, such that the drift is on this order. So the consequence is now we have a perfect match between we have a reasonable match between stability and instability. That is, before this, you have stability over exponentially long time. After that, you can say that Arnold's diffusion switches on, and perturbation theory simply breaks down. It doesn't mean anything. You can't do perturbation theory over timescales which are bigger than that. That's the timescale where perturbation theory simply ceases to exist for good reasons. I mean, it's optimal. So this time scale is optimal. Now, how do you obtain this? Actually, by a method which I won't have time to detail. I mean, if you're interested, we can talk for hours about that. So it's using simultaneous approximation, which is, it replaces, well, at a practical level, all the proofs I mentioned, and since the dawn of time, are full of Fourier series, since Fourier. And even before, I mean, well, by contrast, these are Fourier series free. There are no Fourier series at all. So this is because you don't do this. You do something, well, you do this, but in a very particular case where there are no small divisors. In particular, you replace these quantities by, so this is one form of approximation, the small divisors, and you replace it by what is called simultaneous approximation. depending on your background, you can say that it's projective duality if you're in geometry. Projective duality means you have a duality between hyperplanes and lines. Okay, that's familiar or not so familiar. Duality of projective geometry. You can say also it's the duality. It's what here you have. This is called normal linear approximation. Well, linear simply means that this is a linear form. So here, for people working in arithmetic, there are what is called transfer theorem due to Hünchen. Okay, so these are two forms of approximation, basically due to projective duality. If you're a physicist, you may want to see it as the duality, the wave-particle dualism. It's really connected with the wave-particle dualism. The wave is on the side of Fourier series, and the particle is, suppose you have a torus. I take a point, and I have an omega which is fixed. So the torus is Tn, okay? So it's in dimension n. So it's r mod z to the n. And I let my particle flow. It's just linear on the torus, like this. But it never returns because I suppose omega is not rational, so it never returns. If it returns, it returns. It's a closed orbit. If it never returns, and this, by the way, is called a Kronecker flow, but it's just a linear flow on the torus. So if it never returns, you can ask how long will it take to return to within a small distance, delta, in a ball of radius delta. Well, this is what simultaneous approximation measures. And whereas this is more on the side of Fourier series. So in some sense, it's like wave-particle dualism. And you can even make it a little more precise. Okay, so you have this. And so this is the way to prove things. And which means you, instead of, just in words, instead of saying resonances are bad news, here resonances are bad news, because what are the resonances? They're when the divisors are small. Now you do the exact opposite. You say resonances are good news. So something which is very, very resonant, as resonant as possible, is called a periodic orbit. Periodic orbit is very, very resonant, so to speak, which means omega is a rational vector. It recurs. So instead of trying to avoid resonances, you go for the periodic orbit. So forget the word resonance, because resonance, well, don't forget, but you have to put you in a completely reverse frame of mind. Resonances are not, quote, bad. I mean, they're neither good nor bad, but they're not a hindrance, but they are an opportunity. So you go for the periodic orbit of this flow, not of your unperturbed flow, which is just a linear flow. Of course, this depends on p. Now it's a bit more complicated than that. You go for your periodic orbit, and well, it's the fact that there are many periodic orbits that gives you this exponent. Well, I really want to explain the proof because, well, I'm done, and maybe I could have spoken much more about this, but I think it was also not too bad to have a survey. Here there is something which I'd like to stress is maybe one thing. Stability of resonances. So, which is quite simple. If I have a resonance of, I mean it's also subtle, but if I have a resonance of multiplicity m, okay, so a resonance has multiplicity. If I have a resonance of multiplicity m, I can change 2n to 2n minus m. So if n equals...
Nobody's going to have any idea what you mean by multiplicity here.
Well, the multiplicity of the resonance is... what do you call the multiplicity of the resonance? Multiplicity of the resonance is you're in Zn, what is the resonance? It's omega dot k equals 0. But what are the k's for which this happens? Well, it seems pedantic to say that they have the module, which means simply that. No, it simply means that if I have k1 and k2, and omega k1 is 0, then omega k1 plus and omega k2 is 0. I mean, they're stable under addition and multiplying by integers. This is all what it means. Now, a z mod, something like this in Zn is simply Zm for some n. This is a theorem. But I'm sure you've encountered multiplicities of resonances. There are simple resonances, m equals 1, double resonances, m equals 2, etc. So if you're very pedantic, or it's not unnecessary, you say a free module, a z submodule of a free module is free, and this is it. But I mean, this is a very physical thing. And so then you do this. But if you do this, and what is the dimension, by the way, of a surface, of an M resonance surface? It's precisely this. Z equals n minus n. So for instance, periodic orbits correspond to maximal resonance, which is m equals n minus 1. D equals 1. D equals 1, it's an orbit. Okay, it's just one orbit. So I should say that you change 2n, which is the dimension of the space, to 2d, which means near resonances, you're much more, you're actually much more, and this is, I was really happy about that because there's a long story behind it, which is very, in large part, physical. So, in physical terms, you say, if you're linear, resonance destabilizes your motion. If you're nonlinear, without any friction or anything, I mean, we're still completely Hamiltonian, resonance can stabilize your motion over exponentially long time. And I finish with something which is almost philosophical, but it's not philosophical, it's actually mathematical. K and tori, for instance, live in the very non-resonant part because they are Diophantine. And we said that they're very stable. And here I'm saying that resonances are very stable. So there is kind of a contradiction, but it's not. It's like, in some sense, if you're on the real line, it's the rational points are as far away as possible from themselves. So okay, that sounds very philosophical. If you're a rational point, a rational in Q, then it's not far from itself because it is itself. But apart from itself, it's far from all the others. You see what I mean? And on the other hand, if you're not rational, some vectors, which are like Diophantine, are as far as possible from the rationals. So they are as far as possible. This is being badly approximable. But if you are a rational, you're as far as possible from all the other rationals. Not yourself, of course. Yourself excluded. So it's a very social statement. So any rational being should be as far as possible from all the others, except oneself. No, but I mean, this is serious. But this is complicated. I mean, this is complicated. And probably in physics, I mean, I don't know if there is any hope to really see that. But this is a complicated, somewhat complicated idea in a way. Okay, let me stop here.
You want questions? Or
I don't know. What is it good for?
we have, you don't mind a few minutes for questions?
Oh, no.
For the people who want to leave, please do, because we're over time, but does anybody have questions? Everybody's blank.
Oh, you mean in resonance it's more stable because time is longer.
Yeah, that's what I mean. They're more stable in the sense that the action variable should stay,
Either
are frozen for a longer time in that sense.
one side Km is very non-resonant.
Yes.
So they are very stable. On the other side, the mean motion resonance is also stable because the diffusion time could be.
Yeah, so Km is stable over an infinite time. You could also distinguish between geometric perturbation theory, which finds invariant objects, then you're working over an infinite time. I was happy about all that because also mathematics it's very hard in mathematics to deal with finite time phenomena. Because you deal with asymptotic phenomena. So if you find a torus, it's there forever. It's very difficult to say things which are intrinsic over finite times. And that's what all these things say. They say things which are intrinsic. Actually, they come almost directly from arithmetic and all sorts of things. In that sense, quote, they are intrinsic, and yet they're over finite times. So over over that kind of time, then when you go that Km tori would stay, and all this wouldn't. I mean, after that, wouldn't work. Except it's much more complicated than that because then you have to take into account the threshold of validity. So of course, it's much more complicated. I mean, in real life, it's much more complicated.
Km theory. Can we derive Km theory from the Nekrasov estimation?
No, I'm simply saying.
T time the.
No. What I do here, which is, I mean, much more refined than what Nekrasov was doing, is, I mean, as result, and much more transparent at the point. No, of course not. They're not even, so to speak, in the same place. No, there is a stroke of. All this, what I did and what Nekrasov did, should have been done before Kolmogorov. It's a twist of history.
Yeah, I don't know if it's clear, but the Nekrasov theorem, it doesn't matter whether the trajectories are chaotic or not. It puts a limit that's true in general, independent of the type of function.
Provided
So,
it's like this.
right.
I mean, it's a
Whereas-
perturbation of something.
Right, you don't really care if it's
Oh, yeah,
tori or not.
You don't care. Yeah, true. You don't care
It puts
whether
a
it's.
strong limit, independent of that. Now, if you do have a situation where you have resonances under Kirchhoff's approach, you wind up with the same limit as the Nekrasov.
I think you should say exponential stability.
Right,
It's
a
easier
stability
and
limit
frankly.
rather than a diffusion, which is, it's unstable and it's changing. And the two are the same, actually, if you have a system that's diffusing as quickly. Yes, Bart?
I think this discussion stemmed from an issue which is the simplest you can imagine, at least from a planetary point of view. And that is you put down not two, but three planets of equal mass and equal spacing or some regular spacing. And you begin to move them further and further apart. And you ask, how long does it take for that system to go unstable in the sense that two orbits, let's say, cross,
So
or
that-
two planets
that
approach
thing
each
where-
other. So can one apply these theorems to that problem?
That Alice
And
told.
if so, can you give us any explanation?
Alice told me about the problem yesterday,
So
basically.
this is where the discussion starts.
Yeah, so I mean,
Yeah, that's what I
I
thought.
learned about the
So
problem
what's
yesterday.
the answer? Is there any?
No,
No,
yeah.
well, the answer is if you take the numerical result of Chambers'
Okay.
study, specifically that problem,
Right.
it looks exponential. And
Okay.
I can write the form down, actually.
Am I allowed to
So
switch off?
stability time times the angular rotation rate of the innermost planet looks like some constant. So it looks. So mu here is the planet mass ratio for this system.
Yeah, I'm aware that it
And
looks sort of
delta sets the
exponential.
separation. And so
But
it looks.
but many things can give rise to exponentials. Are you saying that there is a
I
connection?
don't know why
Not
this is
yet.
true.
Okay.
I have no
No.
idea why this is true, or
No.
whether you could adapt some mathematical.
But this is certainly, it sounds like a very interesting.
I see. Okay.
So I noticed that, and that's where
Yeah. But of course I don't know. I mean, of course.
And of course, we hear, you know, sometimes resonance is stabilized in terms of having longer time scales for stability.
I should say that with this proof, the thresholds are much less widely unrealistic than, they're still unrealistic, but they're much less widely unrealistic than for KM proofs. But, you know, KM is difficult then. Just one thing, 20 years ago, we had this the famous, the standard map, and then you had the invariant circles, and then you wanted to prove that the one with the golden ratio would break last. Okay? So I think I can still remember it. Something like this. K sine x. Yeah? True? Yeah, true. Okay, and so the point is, for what K, you have an invariant, will the last invariant circle break? Will the last invariant circle break for the golden ratio and so on? So, well, for the golden ratio, apparently it's okay. So you focus on the golden ratio, then you do that. And then you know that the simulations show that it's for K equals roughly something like 0.97, almost 1. Now, Michel Hermann was one of the greatest people in KM theory. Try to prove this. So this system is, of course, babyish not babyish, it's very important, but very simple in terms of computation a priori. And they tried very hard to do, so this we know, there's even a computer-assisted proof for this by Pierre Cancelletti like 20 years ago. But with the best of his abilities, which were big, which were large, he could prove only that there was 003. So which seems disastrous, but you see, if you ask him when will it break, he would have told you, I don't know. I mean, this is obviously much too small because reality is this. So it simply means that the proof of KM is really not very well adapted for getting reasonable threshold. This one is much better adapted. I think you can reach not really realistic threshold. That's unrealistic. It's an unrealistic hope. But things which are not totally ridiculous, not 10 to the minus 100. Which don't mean anything. I mean, these numbers don't mean anything. They simply mean that the proof is long, cumbersome, and then sometimes you're tired, so sometimes you take 1/10 because why not? And so they don't mean anything. So really one should so much laugh about this threshold of stability because they simply don't mean anything. They simply mean that the person who's been doing the thing by on ink and paper cannot do better or is lazy. They have no intrinsic meaning.
So that they haven't been improved over time?
No.
Oh.
Frankly, I don't think so.
There's the
No, on computers, of course.
No, but this problem with the Nekhorchev theorem not applying, I think it's been improved by the Russian, with the Leningrad group. And I have some papers that I can't understand.
You mean for exponential stability?
Yeah, because the Niederman numbers were just kind of 10 to the minus 14, and so.
They
Alex,
worked on that.
According to Alex said he knew somebody, and so I went and looked it up.
Yeah, because
Yeah, there is. So this is 10 to the
Oh, that's
minus.
interesting.
These
Yeah.
are more optimistic than 10 to the minus 14.
Yeah, I had a student who worked on celestial, planetary problem from that viewpoint.
Antonov
And they got estimates, but of course they were not. First, it was not very real. He was not a specialist of celestial mechanics at all. Only slightly. He was very young with his PhD, and he got instruments which were already like 10 to the minus 14, which is bad. But if you divide by 3, it's immediately 10 to the minus 3. So, a factor 3 can be nothing. For mathematicians, it's just a way of doing things. Sometimes by just changing things, you will get a factor 3, and then, and then it will become completely. I don't know what they did. Now, KM is much worse in terms of threshold because it's much less, it's much less explicit. And there are steps which you cannot make completely explicit.
So you're here for another week, right?
Yeah.
Okay, good. Thanks. Thank you.
Thank you.